Because this example is so long, we've split it over 2 videos. So you need to watch both this one and the next one to see the full example. At 1200 hours, ship A is at the point with position vector 20i plus 10j kilometers relative to port O, and it has a velocity of 10i plus 5j kilometers per hour. We want to find the position vector of A relative to O at 1300 hours, 1400 hours and 1600 hours. A sketch often helps understand the information in the question. So if we draw some axes, and here we have our x-axis and our y-axis, the ship starts at the point 2010. Each hour it will move 10 units to the right and 5 units upwards. So at 1300, that's 1 hour, it's going to have moved 10 units to the right and 5 units upwards to the point 3015. The position vector therefore will be 3015 kilometers. For 1400, that's another hour onwards. So another 10 to the right and another 5 upwards to the point 4020. The position vector therefore is 4020 kilometers. Finally at 1600, that's another 2 hours onwards. It will have moved another 20 units to the right and another 10 units upwards. We now have some information about a second ship. At 1200 hours, ship B is at the point with position vector minus 10i plus 10j kilometers relative to the same port O, and it has a velocity of 20i plus 5j kilometers per hour. We want to show that the two ships will collide if there are no course changes, and we want to find the time at which this collision will happen. Once again, a sketch can help us make sense of the information that we're given. So we'll draw some axes. X-axis, y-axis. The particle starts at minus 10, 10. Its velocity takes it 20 to the right and 5 up each hour. So it's going to go 20 in this direction and 5 in this direction each hour. If we look at its position vector at 1 hour, for example, it would be minus 10, 10 plus 25. And of course it will do the 25 every hour. So the position vector at any time later would be given by RB is minus 10, 10, its position vector at the start at 1200 hours, plus t, the time that has elapsed, times 25, which is the velocity. If you think about this, if t is equal to 1, the particle would be at minus 10, 10, and would have gone 20 to the right and 5 upwards. At t equals 2, it would have started at minus 10, 10, and then gone 40 to the right and 10 upwards. So this should make sense. If we apply the same approach to the position vector for ship A, it started at 2010 and then moved 10 across and 5 up every hour. So therefore we can write 2010 plus t times 10, 5. We can always check t equals 1, which would take us to 1300 hours, t equals 2, which would take us to 1400 hours, and t equals 4, which would take us to t equals 1600 hours, with our answers to part A. If we look at the j direction, we can see that both of them are 10 plus t times 5. So the j components of these two position vectors are always the same. If we now look at the I components and put them equal, so minus 10 plus 20t and 20 plus 10t, if we can solve this, these two particles must crash. We established that their j components was always the same, so if their I component is also the same, they must be at the same point. And this will happen if we can solve this equation. 10t is equal to 30, and therefore t is equal to 3. So we can solve the equation, and they do crash, and they will crash at 1500 hours, or 3 hours after 1200 hours when we started both ships on their journey. You need to also view the next video to see the completion of this example.